These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell these programs, and you may not alter them. These programs are part of a study examining the value of podcasting as an educational medium. If this is the first time you are viewing a program in this optics series, send an email to jyoungmd@gmail.com with your name, your position, your institution, and your city, state or province, and country. Enjoy the podcasts. This first podcast is on index of refraction, and it's the traditional start of the optics lecture series. In order to understand index of refraction, we have to understand that light does not move at an equal speed through all media, and that there are some media that impede the movement of light more than others. As an analogy, let's picture this. This is a car that is approaching a patch of ice, and the driver does exactly what we should not do when we see a patch of ice, which is to step on the brakes. That's right. Okay, at any rate, let's look at the moment that the car intersects the ice, and we're going to draw some little lines and landmarks here. The dashed line, I know this is complicated, a lot of lines and arrows here, but the dashed line that has no arrows, that is at the border between the ice and the area that's not ice, dry pavement. In fact, I believe I can show you this with the mouse. So this area right here, this line, is the interface between the ice and the non-ice, or in optics terms, it's the interface between medium 1 and medium 2. Now, dry pavement for a driver who stepped on the brakes has a greater impedance to movement of that car than ice does. So the medium of the ice is a medium with a low index of refraction, meaning it's a medium that has little impedance to the movement of light. And the dry pavement is, therefore, of course, a medium of high index of refraction, high impedance of movement of light. Now, unfortunately, in optics, we do not describe the border between two media when we're talking about what happens to the ray of light with respect to the interface, with respect to that dashed line. Rather, the landmark that we're going to use, and that we traditionally use in optics, is this line here. It's a line that is perpendicular to the interface, is normal to the interface, and we refer to it as the normal. So we're going to discuss what the ray of light, or in this case what the truck does, with respect not to the interface, but with respect to the normal. Now, this dotted line here was the direction in which the truck was moving. What's going to happen when the driver steps on the brake? The driver's side front wheel is going to have less impedance to movement than the passenger side front wheel. The driver's side front wheel is going to tend to slip, again, because there's less impedance to movement, whereas the passenger side front wheel is going to hang up on the dry pavement. And the car is going to turn. So as the driver's side wheel slips, the new direction that the car is going to take on is going to be the one of the solid arrow. Okay, you can see that the direction of the truck is going to rotate towards the passenger or towards the right. Or in our optics terms, the car is going to be redirected away from the normal. If you see the path that the truck was taking relative to the normal and the path that it's now going to take, it is away from the normal. So we can say a ray of light moving from a medium of high index to a medium of low index is going to bend away from the normal. Now, the situation that we more typically, here it is shown here as the car is veering out of control, but away from the normal. The situation that we face more often in optics, of course, is a ray of light moving through a medium of low index and encountering a medium of higher index of refraction, or in our terms here, moving from a medium in which the movement of the ray of light is relatively unimpeded into a medium in which movement is more impeded, or where the speed of light is in fact slower. This is the case of a skier approaching a patch of gravel. Now, unlike the driver, who was not too bright and stepped on the brakes, the unfortunate skier does not have a lot of options. So he's going to approach the interface between the dry pavement and the snow. And the black line that I've drawn there is the direction, the black arrow that I've drawn is the direction of movement of the skier, which in this case is straight down. What I've done here, using the same symbols as before, is to mark out our landmarks. And again, the dashed red line without arrowheads represents the interface between the sand or whatever it is, dry gravel, and the snow. But we are going to talk in terms of the normal, which is the dotted line that is drawn perpendicular to the interface. Now, the dotted arrow was the initial direction of movement of the skier. His left ski is going to hang up on the gravel, and his body is going to briefly rotate to the left, although obviously in our field of view here it's to the right, but it's the skier's left. So that the new direction of movement is going to be not the dotted arrow, the direction that the skier initially had, but is going to be the solid arrow that I've drawn. And here is the skier on his readjusted path. This is the situation, as I said, that we face more commonly in optics, in which a ray of light is moving through a medium of low index of refraction into a medium of higher index of refraction, and the ray of light is bent toward the normal. Now, let's do this in a way that looks a little bit more like optics and physics and the formulae that we know and love. The index of medium 1, which is the white area, the area on the left, we're going to call n sub 1. The ray of light is approaching the interface between medium 1 and medium 2 at an angle. And of course, the landmark that we're going to use to describe the angle is not the interface, but is the normal, which is the dotted red line that I've drawn there. So the ray of light moving from the first medium is approaching the interface with an angle of theta sub 1, as I've drawn there. It passes through the interface into a medium of higher index of refraction. For example, this can be a ray of light moving from air on the left into water on the right. The ray of light is bent toward the normal. So the case of the ray of light moving from the left side of the page to the right side of the page is akin to the skier moving from an index that is low impedance to movement, like the snow that the skier was on, onto a medium where impedance to movement's higher, the gravel, and as was the case with the skier, whose direction bent toward the normal, so is the case with the ray of light here moving from the air medium, n sub 1, into a higher index medium like water, n sub 2. Just to put numbers on things, air effectively has an index of refraction of 1.0, and water has an index of refraction of 1.33. So n sub 1 here is going to be 1.0, and n sub 2 is going to be 1.33. The relationship as described by Snell's law is that n sub 1 sine theta sub 1 is equal to n sub 2 sine theta sub 2. Now, you can imagine that as theta sub 2 gets larger, theta sub 1 gets larger too. And that we can imagine a situation in which we increase theta sub 2 so much that we get theta sub 1, the exiting ray of light, to just barely skirt the interface. And I've drawn that here. So in this case, we've increased theta sub 2 to the point that the exiting ray of light just skirts the interface, or we say theta sub 1 is equal to 90. Now, I cheated with a previous slide. Let's actually go back to it. I cheated with the previous slide because not all of the light will pass through the interface and emerge on this side. Let's say this is a ray of light coming from the water side, going to the air side and bending away from the normal. This is similar to the car encountering the patch of ice. Not all of the rays of light will pass through this interface. Some of the rays of light will be reflected over here like this. The angle of incidence, meaning the angle of the ray of light as it is incident to this interface here, is in this case theta sub 2. And the reflected angle, the angle of reflection, is also theta sub 2. The angle of incidence is equal to the angle of reflection. So some of the light is passing through the interface and is bending away from the normal, but other of the rays of light are encountering this interface and are bouncing back. Well, what happens here is, again, some of the rays of light are encountering the interface, exiting it, and just skirting the interface. Some of the rays of light are bouncing back, and the reflected angle is, again, theta sub 2. If we increase theta sub 2 anywhere beyond where it is in this diagram, then none of the rays of light will exit the interface. The only rays of light that are incident on the interface will be reflected by the interface and reflect again at the angle of reflection, which also is going to be theta sub 2. We refer to this condition in which all of the rays of light are reflected and none exits the interface as total internal reflection. The angle that is the largest angle at which any rays of light can exit the interface, and that's what's shown in this diagram here, is referred to as the critical angle. So in this diagram, we're going to refer to the theta on the right-hand side there as not theta sub 2, but theta sub critical. So to put numbers on things up top there, we have from Snell's law, n sub 1 sine theta sub 1 is equal to n sub 2 sine theta sub 2. To put numbers on things here in order to discover what the critical angle is, we're going to say n sub 1 sine 90 degrees is equal to n sub 2 sine theta sub critical. And we're going to solve for theta sub critical. And so we're just doing that here. We can say, of course, n sub 1 sine 90. Well, sine 90 is 1. So n sub 1 sine 90 is just n sub 1. So the index of the lower medium is equal to the index of the higher medium times sine theta sub critical. And if we solve for it, then we can say theta sub critical is equal to the inverse sine of the lower index over the higher index. And you can try this, calculate this, please, for water, in which n sub 1 is 1.0 and n sub 2, the n of water is 1.33, which also, of course, is the n of aqueous in the eye.